Now, when the cell becomes energy deficient, the first thing that goes, we now know, is a type of intercellular communication that actually is mediated through microtubules. It's photon communication through microtubules. And that microtubule-based communication is a lead communication between cells. Because after there is microtubule communication, the cells reorient themselves. They actually begin to come together so that gap junctions between the cells can be closed, and that's where the heavy lifting communication takes place. So when microtubule communication is compromised, you don't have the reorientation, and the rest of intracellular communication becomes compromised as well. Now, of course, when intracellular communication isn't working, that means that cells cannot talk to each other. If they can't talk to each other and work together, they can't work well as tissue. And of course, if you have tissue that can't work well together, they can't form organs. And if you have organs that don't work well together, you have a sick organism. So that disruption of intracellular communication is a pathway to explain a whole bunch of different symptoms. Now, the other thing that we now know happens, and again backed up by peer-reviewed research, is that when the active transport channels shut down, nutrients are not able to get in, but also waste product are not able to get out. So now you have a buildup of waste product inside the cell, and among the waste product you have free radicals. Now, free radicals, like those of us from the 60s, love the party, and inside the cell, the party is happening at the mitochondria. So that these free radicals will gravitate preferentially toward the mitochondria, and now you have disruption of cellular respiratory function. When that happens, the cell becomes further energy deficient, and it will become so energy deficient that it will get into a point where the mitochondria will send signals to trigger apoptosis, which is programmed cell death, where a cell will kill itself and commit suicide so a new cell can come in to take its place. Now, that's usually a constructive thing, except the other thing we now know is going on, and Dr. Oberfeld had an example of this as well, is that when free radicals are floating around in the cytoplasm, they interfere with everything that's going on, including DNA repair and transcription from messenger RNA to DNA. Now, when that occurs, you have DNA repair not happening, but you do have within the cytoplasm, within the cell, fragments of DNA that can function well enough to form membranes around themselves. And we call those micronuclei. And micronuclei, when they're inside the cell, are fine because they really don't have any constructive function, but they don't do any damage other than take up space, sort of like the fat cousin who sits on the couch watching TV all day. He's okay, it's ugly, but you know what? It doesn't do any damage. Now, when we have the mitochondria signaling apoptosis, what happens is that the cell membrane disintegrates, and everything that's inside the cell now is dispersed into the interstitial space. Under normal circumstances, a mitochondria in the interstitial fluid will cause a signaling to the immune system that we've got something here that we don't like. The fat cousin has gotten out, we need to call the police. What they do is you have a signal going to the immune system. We need some macrophages here to engulf this thing and take it away. But this is not a normal circumstance, because the cell is energy deficient. The whole area is energy deficient. The signal can't go to the immune system. So now you have a micronucleus that has been released into the interstitial fluid that is what? Energy rich, nutrient rich. The reason is because the nutrients couldn't get into the cell in the first place. So now you release micronuclei into nutrient rich interstitial fluid, and what does it do? It clones and it proliferates, and that is a mechanism leading to tumors. Now, the other thing that we now know happens, which is pretty scary, is that when you have this state of stress at the cell membrane, where the active transport channels are closed down, and as Dr. Oberfeld said, it's a chronic situation, because you have this 8.3 hertz signal that's repetitive. Now you are in a state of constant stress in terms of your cell membrane. The cell membrane wants to be like this. When you have to close the door, it requires energy. It stresses the cell membrane. Things happen to those molecules that require energy to keep them locked down. Now, when you are in that chronic state of stress, here's what happens. In the endomembrane, the protein layer inside the cell membrane, you have messenger RNA. And messenger RNA hang out there to get messages about what's going on outside the cell to carry in to the mitochondrial DNA and the nuclear DNA. When the cell is stressed, it changes the way the messenger RNA folds. So that when now you have new information, because the way the messenger RNA folds is what carries the information, you have now this under stress information going to the mitochondrial and the nuclear DNA. We now know that when that cell goes through normal mitosis, the new information about the cell membrane being under stress is carried to the daughter cells. That means that it's an environmentally induced genetic change. It's an epigenetic change, but it's an environmentally induced genetic change that carries on vertically to the daughter cells. When that happens over several cell cycles, you have a circumstance where the cell believes that it is under siege when it is not. And that is a condition we call hypersensitivity. So that is a mechanism that explains electrohypersensitivity. The disruption of intercellular communication explains all sorts of conditions ranging from fatigue to sleep disorder to unexplained anxiety. And we have the mechanism of micronuclei proliferating in the interstitial space leading to tumors. We found a mechanism that is consistent with all of those diverse conditions. Now, the good news about understanding the mechanism is that now we know where to target interventions. And luckily, there are interventions that now can be targeted at the cell membrane protein recognition response, at the intracellular communication response, and at repairing damage to cell membranes that have already been done. Here's the difficulty. The interventions don't work unless you can eliminate the background exposure. And the unfortunate thing is that while in the old days, and of course this is high technology, in the old days was 2001, in the old days you could distinguish between the near field and the far field in terms of the concentration of these information-carrying radio waves. You could distinguish. Today you can't distinguish it. The reason you can't distinguish it is because you have 2.4 billion people in the world using cell phones. So that every time somebody flips on a phone and the base station is over there, a signal is carried from here to the base station. Here's an experiment you might want to try sometime. Look at your phone and look at the signal strength. And let's say that it's 1 bar. That means this phone has to work hard in order to carry the signal. The harder it has to work, the bigger the near field plume. But here's the experiment. I have a phone with 1 bar. And now what I'm going to do with a device is I'm going to identify where the base station is, which you can do. You can take a device and put it around and figure out where the base station is that this phone is going to connect to. And then line up friends of yours in between the phone and the base station. And what happens is that the number of bars goes up. Because we are great conductors. And what happens is that by sending the signal through us, because we're great conductors, the signal efficiency becomes greater. Try it.